I'm Tim Ventura, and we're joined today by Max Arshavsky, the founder, CEO, and CTO of Zenno Astronautics and inventor of the Zeno Drive. Max studied physics, mathematics, and engineering in Russia's most elite lyceum under the Moscow Engineering Physics Institute, and is a multi-prize winner of the ROSATOM Mathematics and Physics Olympiads. He continued his studies in the University of Auckland School of Engineering, where he concentrated on biomedical engineering and engineering science before beginning his work on Zeno. So Max, welcome. It is a true pleasure to have you with me today. We are talking about the Zeno Drive, which is the world's first superconducting electromagnet for fuel-free spacecraft attitude control and electromagnetic shielding. So I want to start out by asking if you can describe for us what the Zeno Drive is and what your inspiration was for developing it.
Tim, thank you. That's a great introduction. I guess to start with, we've gone away from calling a Zeno Drive the Zeno Drive because people will confuse it with the EM drive. And essentially, technology is very, very different. There's nothing in common, in fact. So we thought, we'll go away from the word drive. We'll just call it Z01, Zeno's first product. Essentially, it boils down to our invention of highly efficient and unprecedentedly strong electromagnets for space applications. And we use superconducting technology to achieve very dense magnetic fields very efficiently. And based on that ability to have, very, very powerful magnetic fields in a very small volume, low mass, and a low power requirement, we can solve many problems. And one of them is spacecraft attitude control or spacecraft pointing.
Okay. Well, so is this only for attitude control? And that would be how the spacecraft or the satellite is oriented towards the Earth, perhaps, or to other satellites. The orientation for attitude control, or does it also provide directional thrust?
Tim, it's a whole platform. So I'm mostly speaking about spacecraft pointing or attitude control simply because Zeno sort of is a mixture between a research and development organization and a business. And as a business, that's our product that we market and we work with people in the industry to solve their problems today. But as a larger sort of endeavor, we see 12 to 15 maybe very impactful applications. And spacecraft pointing is one of the least disrupting from the technology standpoint. It is very disrupting from the business standpoint, but from the technology, from opening the new horizons in space, it is just a better way of doing something that's already being done. But we're also very interested in radiation shielding. That's something that we're starting to work on commercially already. We've just announced a memorandum of understanding with D-Orbit, Italian in-space transportation company, looking to develop jointly radiation shielding technology, in particular to protect spacecraft in geo orbits or high altitude orbits where there's more exposure due to lack of geomagnetic field. Yeah, and we're also looking at reaction wheel desaturation at higher orbits, and we're also looking to propel or accelerate payloads in orbit via, for the lack of a better word, we call it a transfer tunnel, but it really is a coil gun in space. So you can accelerate payloads. You can accelerate payloads without physical interaction with them, with the use of magnetic fields, without any kind of fuel. You can provide them with meaningful delta V and send them on interplanetary orbits. You can send them to Mars, to Moon, keep them in Earth orbit for longer, deorbit things, maybe send them into deep space missions. That's something that is on the horizon for us long term. It's a very ambitious undertaking, but it's very fascinating for us. Yeah.
Well, all of this is exciting. The technology that you're developing is exciting. The reason I asked about attitude control is, if I understand this correctly, and I could be mistaken, but you do have a very powerful electromagnetic field, and you can use that to basically orient the spacecraft or satellite by interacting with the Earth's magnetic field, right? So, but for forward propulsion, you're actually talking about having maybe waypoints that you accelerate through, and that would be kind of the coil gun application. So
That's right. Yeah, interplanetary transfer tunnel system, or in general, transfer system for the solar system, with a number of waypoints where we, accelerate, give an additional delta V, an additional boost to a payload that is not carrying any fuel, or any kind of engine for that matter. Yeah, that's something that we do. With respect to pointing, it doesn't really need to be Earth's magnetic field, as long as it is a external magnetic field. It could be a magnetic field of let's say Jupiter, if we're orbiting Jupiter. As long as we're embedded in the magnetic field, then we can interact with it, and we can orient a spacecraft with respect to that external field.
Yeah. Well, and the only reason I mentioned that was to, waylay any potential comments about, reactionless thrust, or, how would a magnetic field propel itself? In this case, it's not. You're always interacting with something else. That could be a planetary magnetic field. That could be some kind of a coil to, again, accelerate it and add delta V, as you mentioned. Now, I did want to ask, what kind of power requirements do you anticipate this having? Is this something that most satellites are capable of producing? And do you have any concerns about heat dissipation from this system in space?
Those are really good questions, Tim. So we mostly work, commercial applications today for spacecraft pointing are mostly we're mostly concentrating on small satellite market, which is the most common size really these days for the industry. So few tens of kgs to hundreds of kgs to multi-ton. The larger the better. The system doesn't really scale down very well below, I would say maybe 12U would be somewhat practical. Maybe smaller than that would be not practical at all for us. So we're not concentrating on smaller spacecraft. Yeah, and coincidentally, the larger spacecraft, thermal management on those spacecraft is not a problem. So we do dump a bit of heat in the thermal bus of a spacecraft, but it's not much. The power draw for us is on the order of single watts to tens of watts, depending on the size of the unit. That's the power draw, and we're lifting milliwatts to watts of heat from the system to make sure that it's always in a state of superconductivity. So it's quite efficient.
Okay. Well, and to mention this for the audience, and this is on your website, and I'm going to put links to your website in here, but you actually show comparisons to other types of attitude control that's out there. And so one of those that some people may have heard of are like gyroscopic, or basically flywheel type systems, where they're storing mechanical or rotational energy and then engaging kind of a clutch. And in comparison to that, the Zeno Drive has no moving parts. Now, I also saw on the website that there are magnetic systems apparently in use, but yours is apparently more accurate and much more powerful than those, right?
Yes, so there are magnetic systems in use. They're called torque rods. Essentially, the idea from the physics standpoint is not dissimilar to what we're pursuing. Physics is identical, but the engineering is very different. So conventional torque rods are electromagnets, normally with a heavy core, and they generate magnetic field by running a bit of current through a coiled piece of wire through a solenoid. Yeah, so it's a magnetic field on demand. But they use conventional conductors, and there is a huge limitation, when it comes to the size, the mass, and the peak field, and the duration of operation. They're all very, very limited. And as a result of that approach, the existing systems that use magnetic field, they are only used as a complementary system to the primary attitude control system. They're not mostly used these days for desaturation of reaction wheels. So a reaction wheel would, perform the attitude control, and then at some stage you would saturate, meaning that the wheel would spin as fast as it can. You can't spin it any faster. You would then need to de-spin the wheel. But if you just de-spin the wheel, the spacecraft will rotate the opposite way. So you need to take care of that rotation somehow, and it's done by torque rods. Yeah, so we're looking to replace torque rods and reaction wheels on most missions with a single box. I have the box here. For example, a box like this, which is similar to what we've just integrated for launching in a few weeks' time in November. on Falcon 9, is we're looking to compete with torque rods that are approximately, that long, that big. So this is a 15 kg torque rod, 1.2 meters long, I think. Yeah. So there's a lot of mass here. We are building a box to take care of 3 torque rods of that size that are orthogonally positioned. So in one box, we're looking to provide 3 axes of control, meaning that volume reduction is from whatever that is, 1 meter cubed in terms of the volume that is required to accommodate that system, down to this is a 3U, 10 centimeters by 10 centimeters by 30 centimeters, let's say, approximately. Mass reductions on the order of an order of magnitude from 40 kg down to 3 or 4, and ability to operate the technology in orbit indefinitely. That's what we're aiming for.
Yeah, absolutely remarkable. And that is only part of it. The other part of this that I am really excited about is the idea of electromagnetic shielding. And this is something that the Zeno Drive can produce that basically can help shield the spacecraft while it's in space. Now, traditionally speaking, as I understand things, spacecraft, satellites, things like that are shielded by using heavy materials, right? And so if you want to send astronauts to Mars, which is a recent example that I touched on in another interview, you would want to pack basically consumables like water around them to try and absorb as much radiation as possible. But with the Zeno technology, if I understand things correctly, basically you are creating a large electromagnetic field which can help redirect some of those particles that would otherwise cause damage, right?
You're correct, Tim. So the idea is very simple. The idea is that we can protect ourselves in space just like we protect ourselves here on Earth with the use of a magnetic field. So Earth itself has a great magnetic field. We call it geomagnetic field, Earth's magnetic field. And that field is something that A, helps us to keep the atmosphere in place so it doesn't get stripped by the solar radiation, and B, deflects all the charged particles or redirects them in some cases, which is why we have auroras at the poles. But yeah, essentially, magnetic field is a great way to keep life safe, in a particular environment. So we thought we could do. I mean, it's a long-standing sort of approach, from the physics standpoint, that the magnetic fields in space are probably the best way to do it as well. Most elegant, most, from the fundamental sort of from first principles, it is the most efficient and elegant way to do it. The problem has been so far is how to engineer a system that is sane, that is manageable and that is actually flyable. Yeah, and so the invention that we have here at Zeno, Tim, is we use high temperature superconducting wire. Requires approximately, I don't want to nerd out too much, but requires approximately 80 Kelvin, to function, as opposed to 3 or 4 Kelvin, compared to conventional superconducting wire. So high temperature superconductivity, lack of liquid cryogens. Would not use any liquid cryogen in order to make sure that superconductors are operational, and also very efficient ways of energizing the coils. So instead of powering the coils directly with power by wire, we energize the coils wirelessly, meaning that it's very different thermal management profile. It's a lot easier to thermally manage the coils like this, and also superconducting coils. Essentially, you can charge them, with a current. And that current will stay in the coils for a considerable amount of time, generating a good magnetic field without much energy input. So the engineering is quite different. We're just implementing the old idea, the holy grail of how to shield yourself in space, but with modern engineering.
Well, do you think that you could describe this as an initial version of a Star Trek deflector shield? I think that's something that everyone would be familiar with from the TV series.
Deflector shield, yeah, maybe, maybe. It's a cool word. You're the first one to come up with this, so I like it.
Well, the reason I ask is, again, a lot of high energy particles should be redirected around it. Now, I do want to ask, space dust may not have any kind of a charge to it, and photons, right, wouldn't necessarily be deflected enough. So this kind of shielding would only protect against like high energy charged particles, much like the Earth's natural shielding, right?
Yes, yeah. High energy photons will still penetrate. Anything that is not charged will still penetrate. And at this stage, if I'm being practical and looking at commercial applications, it's good for electronics in geo, and we'll need a substantial effort, substantial resource to make it applicable to crewed missions, beyond geo. In particular, so we can shield from the galactic particles that are coming in from all sorts of directions with high velocities. It's a lot more challenging than shielding from solar particles coming from one direction,
Yeah,
with lower
yeah.
velocities.
Still, I think every little bit is valuable. And one of the things that excites me about it
I think it's a really good start.
It's exciting because as I have read about interstellar travel, one of the things that I found is the faster you travel, the more the more damage you take from these particles, right? And so every bit of shielding that you can use in the craft helps, and it makes an enormous difference. Well,
we're also thinking of. Sorry, Tim. Yeah, you go.
So I'm wondering, could this shielding be modified for use on a lunar dome or a Mars colony?
The answer is yes. It can be modified. To use on a stationary sort of outpost on Mars or Moon. I don't see a problem from that standpoint. I know that people are thinking of just throwing a bunch of regolith on top and shielding yourself that way. But I think if you're keen on seeing a bit of sunlight every now and then potentially could be a complementary solution to just protecting yourself with meta, so to speak.
Yeah. And one of the things that, again, most people, I think the media creates some confusion on this, because when you see photos in magazines or TV or the internet, they always show a dome, or they show, landers or buildings on the surface of Mars or the Moon. But when you get into long-term exposure to cosmic rays, right, you really need to go underground. And I know that NASA, for instance, is looking at lunar lava tunnels and Martian tunnels as well. And so your technology, as you've said, it could allow people to get a little bit more sunlight because it would give them more time on the surface.
Yeah, I think it's nicer to be on the surface instead of, dug into the ground.
Well, have you been able to do any testing for this based on the shielding application? Or is there a way to benchmark that based on field strength? I mean, relative to, because I realized that the overall field will be much smaller than the Earth's, but if you have a greater intensity, maybe you can benchmark that compared to how the Earth provides shielding.
Yeah, we're looking at generating thousands of amp-meters squared, of magnetic dipole moment to. Yeah, it's an unusual way to measure it. Yeah, but it's quite strong. So we've just signed, Tim, a MOU with Deorbit, and Deorbit is as I said, Italian in-space transportation leader, really. And we're looking together to do some testing work in Europe in the oncoming year. So we're going to test soon. So far, what we have been doing is we've been obviously testing very actively the approach itself, the operation of superconducting coils in particular thermal environments, in volumetric constraints and power constraints. So we understand that quite well now. And we've done a lot of analytical work on that, but we're yet to have empirical data, on how that particular method of generation, of a magnetic field, how effective it is with respect to real radiation. It's not that it's not that we're concerned about it. It's just that you have to get there eventually, So we know what to expect. I guess I'll keep you up to date, Tim, on the outcome of the tests next year.
Absolutely wonderful material. And yeah, it makes sense that you are focusing on the space movement. Now, if it's okay, this is off my questions list a little bit, but one thing that occurred to me was, if you have superconducting magnets in space, and I think it's amazing that you're able to operate these without using a cryogenic coolant. Have you considered using these for things like docking or couplings or fine positioning of satellites, compared to things that they may have to, like, for instance, maintenance and things like that, where you have to position things in space before you can lock onto them mechanically?
Tim, thank you. That's a good question too. In fact, we do have a partner in the United States, commercial partner, the firm called Arcasys. The CEO there is David Barnhart. Dave Barnhart, he's ex-DARPA director. He is the one who did fly the experiment on the International Space Station called Sphere's Rings. Sphere's Rings were essentially an experiment to show that docking in orbit is potentially, docking of two spacecraft in orbit is potentially feasible with the use of solely geomagnetic fields. So final approach and docking. So, no need for robotic arms and any kind of a propellant, The challenge there was the fields weren't powerful enough, for anything meaningful. And that was done with regular conductors, regular conducting coils. And then, so we've been working with Dave Barnhart and with Arcasys in particular on this for the last few years. We've done a few demonstrations, including for the US Defense on our frictionless test beds to show that indeed it is possible, and also is a great solution for the industry. I would love to see the industry go for the most stable, most clean and sustainable solution, for things like in-orbit assembly and maintenance, final approach and docking. Currently, we do use robotic arms. They're sophisticated pieces of engineering. They're very expensive. They require, sophisticated control, and we complement them with, with thrusters. Thrusters are, very, very tested, very well-known technology, but ultimately they result in pollution, of the spacecraft itself, whether it's charged particle pollution or molecular level sort of pollution. You don't want any of this kind of stuff. Also, you expose yourself to a level of risk of colliding, on approach if you use a thruster. Also not great. If we think about magnets, and we all played with magnets when we were younger, magnets are in the position of natural equilibrium when they are together. So if you have two magnets, they'll turn each other, realign, whatever the alignment is, and they'll dock. So it's intuitively a very natural way to dock in space, provided that we can control the force on arrival, and that's not too challenging with electromagnets. We can alternate the polarity, and we can complement with reaction wheels, to take care of torques, so to speak. But yeah, we're working on it, Tim. It's to our interest as well.
Max, this is absolutely amazing. I want to thank you so much for your time today. It has been a true pleasure being able to speak with you about this. And, again, you guys are looking at work coming up in space in the near future. And so I would love to follow up with you on that once you have a little bit more to share. Let me close today by asking, when do you expect to have in-space test results? Because I understand that's coming up in just a few months, right?
The launch is scheduled for November, at this stage, 25th or 29th. And then we expect some operations early next year. I think we're working with deorbit. So we're in the hands of deorbit, to some extent on how much we can do and when. But from my understanding today, we have two sort of sets scheduled of tests, one early next year, January, February, and then one a few months later. So I think we'll have a fundamental understanding of how things are looking early next year, and we'll announce whatever we observe. We'll announce. So we'll do some health checks on the system. We'll try to cool it, and expose the results.
Wonderful, Max. Let me thank you again so much for your time today, sir.
Jim, thank you very much. My pleasure.